Then comes the important aspect of Spark workloads, which is called Spark Shuffle Storage. Now here we are talking about an approach using the NVMe SSD storage options. So what exactly NVMe SSD? So it's a non-volatile memory express protocol to connect to the solid state devices on the EC2 machine. So this is not available on every EC2 machine, only specialized EC2 machines provide this capability. So for example, if we have a EkS worker node with which is called C5D.xlarge. So D is a specialized instant type which provides SSD storage. Now on this node, we have two executor pods, 1 and 2. Each of them are using 10 GB memory to run the workload. Then they need the SSD memory mounted at /mnt /kits hyphen disk. So the local storage for the executors is coming from the SSD. So this is where the Spark storage is used. So that means it is providing very high throughput and low latency use case. Similarly, you have one more worker node which is C5D.12x large, and here we have similarly two parts, and both of them are using 10 GB memory, and in this case we are using a different configuration called RAID. So in this case, one or more SSD disk can be combined logically and create one mount path, which is /mnt/kits-disk. So applications will be using only one path, but under the hood, two different disks are used, chained together. Okay, and from the application configuration point of view, you will be creating a host path configuration for the volumes and using this path /mnt/kits-disk to reference this SSD disk. So applications will be writing to this. The shuffle storage will be going into this disk, providing high throughput and low latency. And for the permanent storage, applications can leverage S3 bucket for input and output, or any temporary data as well if required, but primarily it will be used for the permanent storage. And the advantage of this approach is to basically to increase the high throughput and reduce the latency for shuffle operations. So we are using both the memory, the RAM, and as well as the high performance SSD disk for storing the shuffle data. So this is one of the options to improve the performance for the Spark workloads. Then there is one more option if you want to use the Amazon EBS for the dynamic allocation of the PV and PVCs. So in this case, we have one worker node which is C5.xlarge. So this is not a specialized instant type like earlier where we have C5D.xlarge, but this is a normal Nitro instance C5.xlarge. And here some executor parts are running with the 10 GB of memory, and they require, for example, EBS throughput, for example, 4.7 Gbps, and they will allocate the PV and PVCs dynamically through the CSI driver for the EBS, and two EBS volumes are allocated, each is of size 40 GB. Similarly, one more worker node which is a larger size C5 12x large, and here also we have two executors using the same memory configuration, but the EBS throughput is different, which is 9.5 Gbps, and there also we create two different EBS volumes of 40 GB size. Now again, S3 bucket can be used for the permanent storage, and here the advantage here is if you have a variable throughput requirement for different jobs, then you can configure the respective EBS volumes accordingly. And we can also leverage the persistent volume claims like we discussed earlier, where the driver pod can own the PVCs and retain and reuse for different executors. So every time an executor starts, you don't have to create a new PVC. So that is the configuration. So obviously we are not providing any static configuration, it's a dynamic configuration. Then comes the compute, which is also very important design criteria when it comes to running Spark workloads. It's always recommended to run the Spark driver pods on on-demand EC2 machines because the driver pod needs to be running all the time throughout the job execution. And apart from on-demand, you can also leverage the reserved instances, which can provide further cost savings up to 72% on top of the on-demand pricing. And for executor pods, we can leverage EC2 spot instances, which will provide up to 90% discount on top of the on-demand. And Spark inherently provides the resiliency if one of the executor pods gets terminated due to spot interruption, and that job can recover the node failures or the pod failures. So that's why Spark executor jobs can be run on spot instances as well. And with respect to the architectures, we have both Intel and Graviton. Within the Graviton, we have both the Graviton 3 and Graviton 4 family of processors. Each provides different price and performance characteristics, so customers can leverage that as well to reduce the cost and improve the performance. From Intel instances, typically there are three types of instances. One is the general purpose, which is M series, and second one is memory intensive, which is R series, and the third one is a compute intensive instance type, which is C type. But how do you decide which instance type do we need to use for the applications? So the way to determine is basically to take the CPU and the memory ratio for the request configuration in the pod specification. For example, if you have a pod which is required 100 millicores of vCPU and 200 MB of RAM in your request configuration in the pod specification, that is 100 is to 200 is basically 1 is to 2. So that means it is a compute intensive application. So C type is a preferred instant type. Now, if the ratio is 1 is to 4 or more than 1 is to 2, then it will be general purpose. M series is optimal. And for 1 is to 8 configuration, it will be R series. So this is how you determine the instant type based upon this ratio and create the nodes accordingly. Now there is one more option in Spark with respect to uh, adding some extra buffer for the memory overhead scenarios. So there are two options. For example, if you are using any Scala based Spark workloads, minimum of 10% is recommended, and for any PySpark based application, minimum 40% for executor is recommended. And the field which is used for this configuration is memory overhead factor within the Spark.Kubernetes namespace. Then let us discuss the Carpenter node pool. And Carpenter is highly recommended Kubernetes cluster autoscaler for data processing workloads because of the various benefits it will bring in terms of the speed at which it brings EC2 nodes by directly talking to the EC2 Fleet API instead of going via autoscaling group. And it also provides a lot of bin packing capabilities and also provides a lot of cost saving benefits by consolidation feature and provides very powerful scheduling capabilities which Kubernetes offers and also custom scheduling options. So in the Carpenter, there are multiple CRDs. One of them is the node pool concept. So since we discussed for Spark driver pods, it is recommended to use on demand, and for Spark executor, it's recommended to use Spark. So the configuration for the node pool object will look like this. So in this case, we are creating one node pool object, and we provide spot and on demand as options for the capacity types, and then it will also provide configuration for instant types. So in this case, we are using R6, M5, and C5 GD. So specialized instant types we are using it depending upon the use case, and it will also refer to one more object called node class reference that we will discuss in a minute. So this is one of the very sample configuration for the node pool, and this is available from Carpenter version 0.32 onwards. The next one is Carpenter EC2 node class, one more object which defines the configuration for the underlying EC2 node that Carpenter brings when the pods are scaled. So the configuration looks like this. Here we are talking about the user data section to further configure the EC2 node while bootstrapping. Here the RAID configuration is provided here, which means multiple SSD disks can be chained together, combined together to provide a single logical mount path for the Spark Shuffle storage use case that we discussed earlier. And while using the EC2 Spot, it's always recommended to enable the Spot interruption with Amazon SPSQ, which means Carpenter inherently handles the spot interruptions and take the appropriate action by draining the node and evicting the parts and then creating a replacement spot instance. All of this is handled very seamlessly and efficiently by the Carpenter, which means we don't have to deploy any other node terminal handler or any custom automation required to handle these interruptions. And sometimes it may be necessary to have some Kubernetes bash schedulers, like they provide various functionality based upon the queuing based or priority based or gang scheduling, right? For example, gang scheduling typically ensures that the required resources are available before deploying the job, right? And some popular options in this case is Unicorn and Volcano. So this is also important to consider depending upon the use case. Then comes the metrics. Since we are running the workloads at scale, it's important to have a strong monitoring stack for tracking the metrics. So for example, we have a cluster where the Prometheus is running inside the cluster, and we can use Amazon managed Prometheus service called AMP, and we can also leverage the managed Grafana service called AMG. And when the data engineers submit the jobs to the cluster using the Spark Submit API, and the driver pods gets created, which in turn create the executor pods, and the metrics are exposed at a certain endpoint, and these metrics will be scraped by the Prometheus and sent to the Grafana and dashboard. So you can use either open source based Prometheus Grafana stack, or you can use the managed services as well. And apart from that, Spark also provides a powerful feature called history server, where you can monitor the stacks, the various the Spark jobs execution progress, right? For example, you have EkS cluster where you also configure an S3 bucket for storing all the Spark event logs, right? So this is a sample configuration, and you deploy a Spark history server within the cluster, and you created an ingress object. So that means an ALB is created to expose this Spark history server pod. And when you deploy the Spark applications inside the cluster, driver and executor pods are created, and their respective log events are sent to the S3 bucket. And then when the user looks at the UI to monitor a particular job, the logs are fetched from the S3 and shown in the UI. So you can track all the different stages of the application execution and how much time each step is taking or each phase is taking and how many executors are there. All of that can be found in the history server, which is very powerful in terms of the debugging aspect. For Spark logging, it is recommended to use Fluent Bit as a demonstrate mode, where it can scrape the logs from the various containers in the node and send them back to the logging destination, which could be CloudWatch, S3, or any other external logging solution. And one important thing we need to keep in mind for the Fluent Bit configuration is the extra filters config, where the use kubelet option is equal to true, which means when the Fluent Bit decorates the logging data from the pods, it requires a metadata about the Kubernetes object, right? For example, pod. And without this option, the use kubelet is equal to true. What happens is the Fluent Bit will go to the API server, makes many API server calls to get the data, which increases the latency and also affects the throttling of the API server. So instead of that, it can use the local kubelet endpoint to get that metadata, because Kubernetes is anyway managing that pod and it has all the metadata required without the need to go to the AWS server. So this is a very powerful and efficient configuration need to use when you deploy the Fluent bit. So when you deploy the applications in the cluster, the driver pods are running on the node and their logs are being consumed by the Fluent bit and sent to the respective destination of choice. Now, so far we discussed the various deep dive aspects of running the Spark workloads on Kubernetes. We discussed why Kubernetes in the first place, how does Kubernetes offers for the data processing workloads. Then we had an introduction to the data on EkS, what open source based data platforms we can create. Then we went into deep dive of how Spark works in Kubernetes in general. Then we saw some of the best practices. Now it's a time for the lab to see how to put together all of this and see them in action. Let's get started.